Imagine a wandering giant, lost in the dark heart of the Milky Way, with no mother star to warm it, illuminate it, or guide it. A solitary colossus that drifts some 20 light-years away, close enough to count as our cosmic neighbor, yet exotic enough to shatter every expectation of how a planet should behave. This titan answers to the awkward name SIMP-0136, but don't let that clumsy label fool you. What it holds is simply a banquet of surprises that defies astronomers' understanding and blazes a trail into the new frontier of research on starless giant worlds. SIMP-0136 lives in perpetual darkness. With no nearby star, its atmosphere glows only from the infrared energy it emits, an ethereal, faint light decoded by powerful telescopes. On a galactic scale, 20 light-years is but a single city block, and yet for a long time, SIMP went unnoticed, masked by its own shadow. It wasn't until 2006 that an infrared observatory bearing the same name, the SIMP survey, revealed the object, placing it among the brown dwarfs, bodies too massive to fall into the category of giant planets, yet lacking the heft needed to ignite nuclear fusion and become a true star. Consider for a moment the numbers that define this monster. 13 times the mass of Jupiter, nearly 17,000 times the mass of Earth, a diameter capable of swallowing our planet over 100 times, and, crowning all, a rotation so astonishing that one day passes in a mere 2 hours and 24 minutes. To visualize it, if we lived on its gas-shrouded surface and somehow survived those extreme conditions, we'd see the horizon sweep by as swiftly as a second hand on our clock. A sunset every hour, a sunrise every instant. But why do we care so deeply about a world that is neither star nor classic planet? Because it is a living laboratory. Without the blinding glare of a host star, SIMP reveals its atmospheric backstage with unusual clarity, exposing clues about storms, metallic clouds, and colossal magnetic fields, phenomena that, on more conventional exoplanets, lie hidden behind stellar brightness. Move ahead in the timeline to 2014, when the Spitzer Space Telescope and the legendary Hubble turned their instruments toward the object and discovered its infrared glow pulsing at regular intervals, evidence that dense clouds whirl at breakneck speeds in the upper atmosphere. These pulses were so perfect and repetitive that any deviation signaled a violent storm, a colossal dark spot, or gigantic bands of metallic clouds passing before the lenses, as though Jupiter itself had been magnified and cranked to full speed. 4 years later came the real watershed moment. In 2018, radio telescopes at the Very Large Array in New Mexico detected radio emissions coming from SIMP-0136. For the first time in history, astronomers directly measured a powerful magnetic field on a body that orbits no star. Measurements revealed an intensity surpassing Jupiter's own, already the solar system's strongest magnet. This discovery vaulted the object to instant fame among exoplanet hunters, signaling something unprecedented. If we can trace magnetic fields via radio waves, we may detect far-flung exoplanets, even those that do not reflect starlight. And where there's a strong magnetic field, there are auroras. But unlike the green and purple lights that dance over Earth's polar skies, fueled by the solar wind, SIMP's auroras need a different energy source, since no star is showering it with charged particles. The leading explanation is that its absurdly rapid spin acts as a natural dynamo, generating internal electric currents that excite the magnetic field and produce the dancing lights. Imagine vast electric curtains tinting the atmosphere in sapphire and violet, pulsing relentlessly every 2 hours. Then we fast forward to 2025, the year the James Webb Space Telescope, supreme master of infrared vision, entered the scene. If Hubble was our window to visible light, Webb functions like cosmic night vision goggles. It pierces dust, senses heat, and unveils hidden layers in clouds that to optical telescopes seem completely opaque. The scientific community seized upon SIMP-0136's brief day and watched it continuously for 2 Earth days, enough to witness 20 full rotations. The result was a fleeting spectacle of colors: deep red, golden yellow, electric blue. Each hue told its own chemical tale. The red bands revealed clouds laden with iron particles, burning internal energy and casting sanguine reflections into space. The yellow patches, higher and denser, displayed vaporized silicate, glass dust, so to speak, hovering where on Earth you'd expect only water or ice. The intense blue around the poles corresponded to the auroras detected years earlier, mixed with hotspots boiling beneath the atmosphere, suggesting regions where internal heat jets convectively tear through cloud layers. Specialist observers soon noticed a fascinating anomaly. The speed at which these colors swapped places fit no current atmospheric model. Clouds alone do not reorganize in minutes. Colossal silicate storms do not dissipate in a single rotation. Color shifts this rapid point toward even more extreme processes or phenomena never before seen. Perhaps pockets of carbon dioxide rise from the depths and condense almost instantly, or internal currents sweep across the skies like supersonic hurricanes. Some even point to the aurora itself, capable of altering the color signature when energetic particles collide with different gases in the upper atmosphere. Now pause and reflect. If a single wandering body with no star hides metallic storms and self-powered auroras, what might we uncover in systems brimming with gas giants, brown dwarfs, and planets beyond imagination? Every piece of data we extract from SIMP 0136 is a fragment that fits into the exoplanet puzzle. It offers us, gratis, an instruction manual on how to detect dynamic atmospheres, magnetic fields, and brightness variations on distant worlds, all without a star's blinding glare hampering our measurements. If you find the notion of iron and glass clouds racing around at over 40,000 kilometers per hour extraordinary, imagine witnessing auroras illuminating a sunless sky, powered solely by magnetic discharges. It's the ultimate demonstration that nature loves to break patterns. Not every planet orbits a star. Not every aurora requires solar wind. Not every sky hinges on water, nitrogen, or oxygen. And here lies the irresistible narrative of exploration. By gazing at SIMP 0136, we peer into almost poetic possibilities. Perhaps civilizations exist on giant worlds orbiting dead stars, or research bases sit anchored on brown dwarfs, harnessing internal heat instead of sunlight. Studying rogue objects also deepens our understanding of how planetary systems are born and dismantled. Some of these bodies may have been violently ejected from their original systems after gravitational dances among newly formed gas giants. Others might have formed as failed stars, missing the nuclear ignition by mere fractions of mass. All this fascination converges on a single message. If we aim to unravel potentially habitable exoplanets, we must first decode extremes like SIMP 0136. We need to master analyzing turbulent atmospheres, hunting magnetic fields by radio, and interpreting heat pulsations in darkness. Every technique honed on this natural laboratory will be applied to Earth-sized rocky worlds hidden beneath the glow of dwarf stars, where signatures of life could be as subtle as a slight infrared color shift. So here's your invitation. If you're into these boundary-pushing astrophysical journeys, don't let this story slip by. Click subscribe now. Ring the bell so you won't miss our next cosmic expeditions. Leave a like to boost the algorithm and bring this content to more curious explorers, and share it with that friend who always wonders what it would be like to travel beyond our solar system. In the comments, tell us what intrigues you most: starless auroras, frenetic rotation, or boiling metal clouds. Have you ever imagined a civilization on one of these mysterious wandering worlds? Your participation fuels the debate and helps strengthen science within our community. Because in the end, studying SIMP 0136 is like looking into a distorted mirror of our own future. Earth, too, will one day drift without its sun, when our life-giving star reaches its final stages. By understanding the weather, magnetism, and ever-shifting colors of this cosmic vagabond, we're, in a way, mapping what happens to worlds condemned to eternal night, and perhaps anticipating the technologies our descendants will need to face the vast interstellar chill. Thank you for watching, and see you in the next video.